Good morning. Thank you for those who joined us. Today's Grand Round, we're going to take a slight detour from the classical surgical science research and looking at the new aspect, slightly different aspect of environmental footprint of healthcare and delving into the net zero healthcare angle. And I remember when I was doing first year of my surgical training, I went to watch a film called An Inconvenient Truth by Al Gore. And it was one of the first sort of instance which climate change kind of really hit the note in the back of my mind. And interestingly, halfway through my career, now I find myself doing research into the net zero environmental sustainability aspect of healthcare. And today we have with us Dr. Scott McAlister, who is a senior researcher based at Sydney, and he has multiple affiliations, both with University of Melbourne and University of Sydney. He and his team has really been one of the pioneers into research on aspects of environmental impact of healthcare service delivery, and his works really catalyzed some of the later international collaboratives that which I'm leading now, and I'll share with you later during the talk. So please can we welcome Dr. McAlister.
Hi, thanks Regent for the opportunity to speak. So this work actually came out of us doing a footprint of a patient in ICU with sepsis, and we realized that pathology testing and diagnostic imaging, we actually had no idea what the carbon footprint was. So that was the catalyst for this work. I'm going to start off just actually framing this with this idea of carbon budgets. So it's only been recently, so about 2019, that scientists have found a near linear relationship between cumulative CO2 emissions and temperature change. And it's really important to realize with carbon emissions that in terms of a human timescale, you can consider them to be permanent. So there's other gases like methane, which are only short acting in the atmosphere. But a kilogram of CO2 that goes into the atmosphere is going to be up there for centuries to millennia. And it's going to shift around eventually to different carbon sinks, so to land or to oceans, but we can consider them to be permanent. So with that in mind, we've got this idea of carbon budgets. So if you look at 1.5 degrees, which is the Paris Agreement, that we want to keep warming to that level above pre-industrial levels, then we have a remaining carbon budget. So currently we've got about 1.2 degrees warming of the 1.5 degrees, and it's predicted over the next, before 2030, there'll be some years that we do actually exceed that 1.5. So got a smaller remaining budget. We also, as I mentioned before, have non-CO2 gases that have a warming impact. So we've got things like methane, and for healthcare particularly, we've got nitrous oxide and some anesthetic gases, particularly desflurane. And so we want to keep warming below the 1.5, then we actually have to factor those in too. There is some earth feedback mechanisms as well. So things like Arctic ice. So as that starts to melt, less heat gets reflected back, more ice melts, which means less heat gets reflected back. So the remaining carbon budget we have is actually quite small. And it's really important to realize that if we keep on emitting carbon, then the temperature keeps going up. Which is why this idea of net zero is not sort of an aspirational, no New Year's resolution, I'm going to run my 5Ks. It's not that aspirational thing. It is this absolute thing. If we don't keep stopping CO2 from being emitted, then the temperature keeps going up. And these temperature rises have quite big impacts. So for temperature, not only do we have greater intensity, so things get hotter with these quite small changes in global temperatures. You can see from the graph, from the diagram, sort of between 1.5 and 2 degrees, not only are things hotter, but they become more frequent as well. And that's true for precipitation, so for heavy rain events, and for droughts. So where are we headed? This is the IPCC. These are some shared social economic pathways. And this is where we're headed. So by the end of the century, we're going to be between sort of 2.5 and 3 degrees above pre-industrial levels. And if you think about those previous diagrams, the very small changes of temperature have big changes in outcomes. So because of this, the IPCC, their latest report, made the statement that if we're wanting to limit warming to 2 degrees, we need to have immediate reductions in all sectors in this decade, with the important thing of being all sectors. So globally, healthcare is responsible for about 4.4% of annual greenhouse gas emissions. In the UK, healthcare is responsible for about 5%. Australia, where I'm from, is about 7%. The US is about 10%. So in Australia, just to kind of put that in context, the building industry is about 12%. So 7%, 12%. No, healthcare is a major emitter of greenhouse gas emissions. And there are health impacts due to climate change. So heat waves. We've had heat waves going over Europe this last summer. There's a paper just out at the end of last year that said the heat wave in Europe over 3 months in 2022 was responsible for about 62,000 excess deaths from heat-related mortality. We know bushfire smoke increases mortality, and flooding, apart from those direct impacts of flooding, such as drowning, you get these increases of waterborne pathogens. We're getting increases of vector-borne diseases. So mosquitoes, we're seeing that in Australia with some diseases that only used to be in sort of far North Australia are starting to head further south. And really importantly, that gets lost, but it's actually a really important health impact, is undernutrition. So climate change will decrease agricultural yields, fishery yields as well, because of warming temperatures in oceans are seeing these decreased yields. Now, when people think of carbon impacts, in healthcare, people tend to go to these two things. So they go to buildings and waste, but they're only about 15% of the total emissions. And about 60% is the stuff that gets used in healthcare. There's only limited if you look at the majority of things that get used as consumables, you've got plastics, you've got metals, plastics at their absolute, so 100% renewable energy over the whole supply chain recycling. You can reduce emissions by about 50 to 60%, so that they still come with emissions. With metals, especially things like steel, the possible reductions are even less, maybe 10, 15%. So it means that you can't rely on technology to reduce impacts. You have to actually start changing clinical practice. But to do that, we need to first determine what are low carbon interventions. And life cycle assessment is a way of doing that. So first up, what is a life cycle? So it's this idea of these interlinked stages. So we start off with raw material extraction, so from things like from mines, from forests, from agriculture, getting those sort of raw materials. You make them into things. So from gas, you get plastics. From ores, you get metals. Get made into parts, assembled, used, and then you have the end of life. So it either goes to landfill, or is incinerated, or maybe gets recycled and joins the circle again. And this life cycle approach is really important, that we take this whole big picture approach. We tend to focus on things that we see. So it's why there's been lots of assessments of packaging, because we see the packaging. We don't tend to think of the things that are within the packaging. It's also really important because we tend to see things, if we focus on things on one stage of the life cycle, then you can shift burdens to other parts of the life cycle. So if you say in the use phase, I'm going to do this to reduce the burden, it might actually increase the burden at the end of life, or during assembly, or shift the impact to other impacts. So as an example, I'm talking here mainly about carbon, but there's a whole other range of impacts. So in reducing carbon, we might actually increase water use substantially. So that's why this whole big picture approach is really important. So life cycle assessment is starting to quantify these emissions. So you've got this idea of the economy or the technosphere, and you have things that are coming in from the environment. So you've got these resources, you've got water, you've got land use, and then you have things coming out of the environment. So you've got carbon dioxide, you've got other emissions to air, you've got PM 2.5 as an example, you've got emissions to water and to land. And life cycle assessment is looking at these this interface between nature, with things coming in and things coming out, and is quantifying those flows. So the main way we do this is something called process LCA. We have a whole range of these individual little processes. We've got things coming in. We've got energy. We've got materials. There could be raw materials from nature. There could be materials from other processes. We've got things coming out. We've got products. We can also have co-products, and we have emissions coming out to the environment. And a really good example of this is a sheep. So we have inputs. We have fertilizer for the pasture. We have diesel for tractors and other farm machinery. We've got these two outputs. We've got the main one, this is the merino sheep. So we've got the main product of being wool. We've also got meat, and we have emissions such as nitrous oxide from fertilizer and methane. And of course, when we do this, LCA goes into a whole heap of detail. So it's looking at both emissions and where they're going. So whether it's going to groundwater or to rivers or to oceans. And then we have a thing that comes out of this called a process tree. So this is for a UNE blood test. This process tree is heavily truncated. It's got about 1,000 individual processes, and you can think of it as a pyramid. So at the bottom, you've got those raw material extractions that are coming up to the final thing, which is the blood test. And so if you have a look at the diagram, you can see we've got plastics coming in from collection tubes, nitrile gloves, and on the right, you can see what happens in the lab. So electricity and other consumable test equipment. There's two types of LCA. There's attributional and consequential. So attributional, you can think of a big pie, and what you're looking at is the slice of the pie. So if we have a hospital, then an operation is responsible for this much of the hospital's CO2 emissions. Consequential LCA has a different sort of idea. It's looking at what is the consequence of either an increase or decrease in demand. So a good example is what is the consequence of increasing electric vehicles? And so you may get a decrease in the amount of petroleum extraction, so less oil sands that are being extracted, but you get an increase in mining for rare earth metals and copper. So there's different ways of looking at this consequential, but a train is a really nice way of looking at it. So if we have a train that emits 100 kilos of CO2, and then you have 5 people that hop on, the attributional, each person is responsible for those 20 kgs of CO2. So it's like their slice of the pie is 20 kilos of CO2. For consequential LCA, on the other hand, the train's running regardless of anyone is hopping on or not. So when the person hops on, the engine has to pull a tiny bit more because of the extra weight of each person. So you can say that each person is responsible for 0.5 kilos of CO2. So hopefully you can see some of these differences between attributional, the share of the pie, and consequential, what actually kind of happens in reality. And there's a time aspect and sort of a scope aspect. So you might go, what is the consequence of 10,000 people ditching their cars and hopping on a train? And the consequence could be we need to build some more trains and we need to build more tracks. Which leads us to the carbon footprint of imaging, which was a paper that we got published in Lancet Regional Western Pacific last year. So we looked at CPs, MRIs, X-rays. So we focused on chest X-rays and ultrasound. And we asked, what is the average carbon footprint? So that's an attributional approach. And we also looked at the consequential approach, which was, what is the carbon impact of performing an additional scan? And we have this idea of a functional unit, so the function that you're describing. So a CT, CXR in an Australian public hospital, or an additional one in an Australian public hospital. We have a system boundary because we need to sort of draw a circle around what we're going to measure, because otherwise we get into the machine that makes the machine that makes the machine. So we have to draw a boundary around things. So of note is air conditioning and heating and ventilation. We excluded that from the study, and we did that because we know from other studies. So from that ICU study is a good example, because we compared our ICU with one in the United States. That heating and ventilation is like very seasonal. That's the energy that gets used is very seasonal, and it's very location specific. You also have the thing of CT and MRI rooms need to be kept cool, depending on sort of the set point of the hospital cooling, whether that's 21 degrees for the hospital or 23 degrees in those general areas. That actually also affects how much the scanning room needs to cool down. So because of those variables, we wanted to exclude those so we could just focus on the actual scanners. We also excluded the manufacturer of the scanners and all the kind of the infrastructure. And we did that because we did sort of a back of an envelope sort of calculation, looking at what is the impact of a scanner from various sources. And we realized that based on the machine life of sort of that 10 to 15 years, the impacts per scan were tiny. And that's true for a great deal of sort of those infrastructure types of things. So oil and gas, or power stations. We measured electricity for each scanner for a period of 2 weeks. And we ended up getting, this is power consumption of a CT scanner. And you can sort of see a few things. So down here is where the machine was turned to a low power mode overnight. So CT machines were never turned off, they were turned to a low power mode. This point here is like 7:30 in the morning when the staff come on and they get the machine up and running to the sort of more active power mode. You can also see that there are some days like this day here and this day here, but actually there wasn't that much scanning compared to days like these ones here where there was a lot. So these big spikes here are the actual scanning. So if we look at that from sort of a shorter time frame, then this idea of here's this sort of standby overnight, and here's this active standby where the machine's just waiting for the patient to walk in, and this is the active scanning. So when we looked at the attributional, if you go back to the train example, we took the total energy. So we included this overnight energy, this active, the scanning energy, and all the standby energy. We looked at absolutely everything. We combined all of that, and then we divided by the minutes of active scanning, of active imaging. And so we got this power usage per minute. For consequential, if you think back to the train runs regardless of whether there's anyone hopping on or not. The same for these scanners, they're sitting in the hospital. So 7:30 in the morning, they get turned on. If no one walks through the door, they're still going to be turned on. So what we did was we averaged this the scanning, and then we took away the standby, if that kind of makes sense. So we were just looking at the average here minus the average here. We also included all the consumables. So this is for CT. So gloves, cotton sheets that get used between patients, the washing and drying of those, syringes and contrast. And here are the results. To two things really stand out pretty quickly, and that's the attributional MRI and CT. I should say these numbers up here are the equivalents of driving in a passenger vehicle. So these are so great especially because of that standby power and that standby power overnight. So the machines are sitting in standby, being kept sort of cool between sort of 6 o'clock and that 7:30 in the morning. And so that results in all this electricity being attributed to it. CT machines can be turned off overnight. MRI machines can't, because the magnet has to continue to be cooled. As soon as you drop down to the consequential, then the impacts drop considerably. So the consequence of doing an additional MRI or CT is actually quite tiny. For X-rays, the majority of the impact came from consumables, and especially things like that cotton, those cotton sheets and pillow slips that get laundered. The actual power impacts for an X-ray machine are quite tiny. And for ultrasounds, compared to the rest of the modalities, is also quite small. So how do we reduce emissions? So renewable energy is really important. We can't wait until the grid is 100% renewable, though. If you think about that, if we go back to the idea of the remaining carbon budget, every kilogram of CO2 we can stop getting into the air is really, really important. We can develop low energy scanners, and that's starting to happen with scanner manufacturers. They're starting to they recognize the power usage of scanners is really important, and so they're starting to develop low energy scanners, and especially the standby power overnight. So that's starting to happen. Turning off scanners whenever possible. So for MRI machines, you can't do that. For CT machines, that's possible. So especially in hospitals, where there are multiple CT machines, it's possible to leave one on for emergencies overnight and turn the others off. Reducing unnecessary imaging is really important. So in Australia, as an example, about 40% of imaging for lower back pain is unnecessary. And there's a range of other types of imaging that is unnecessary. You can substitute low carbon modalities when possible. So a good example of this is using for shoulders. You can use ultrasound instead of MRI and get the same type of information. Also increasing scanner utilization. So the idea that when you have a scanner, you make sure that it is being really, really utilized. As soon as you buy a new scanner, it comes with that whole sunk kind of energy cost from that standby power. Overall, if you're thinking about carbon neutral healthcare, we need to consider that treating people today will result in morbidity and mortality in the future. So in terms of intergenerational equity, we need to ensure that we try to reduce carbon as much as possible. Healthcare is always going to have a carbon impact. It's impossible for it not to. But it's really important to significantly reduce the emissions so those remaining can be offset with things like forestry credits as an example. And to do this is going to require a multidisciplinary effort. It needs clinicians, it needs the engineers and manufacturers making machines, it needs policy makers and health economists.
Well, thank you. Spot on time. So I'm Regent Lee. I'm been with the department for 10 years and particularly proud to present some of the latest work today in front of my parents in the audience who dialed in from Australia. And following on Scott's presentation here, we want to showcase how clinicians could help participate in this effort to reduce carbon footprint in healthcare, and also developing some of the lower carbon impact technologies in radiology. And here we focus on CT imaging as the exemplar. And most of you know what CT scan is. What you probably don't know is a lot of them the number of CT scans being done per year, 300 million globally. And out of these, about 60% requires contrast imaging. And we need contrast imaging for a variety of reasons, and which means 180 million CT scans per year have contrast injection. And this is the conventional imaging pathway, CT imaging pathway, when you require contrast, needle in the arm, go in for the first injection, have that non-contrast CT, which is mostly required so they can time the injection of that contrast, and the patient goes in the second time to obtain the actual contrast CT scan. We know as clinicians that this needling and contrast injection aspect can create problems. The needling itself is uncomfortable. My mum survived breast cancer 25 years ago, and she essentially had no veins left in her arms. Can't get a needle in her easily. And the contrast injection can cause toxicities and inflammatory reactions. Importantly, it creates a lack of healthcare resilience. The supply chain can become a problem. And you might remember during the COVID period, 2-3 years ago, the contrast manufacturing plant in China shut down, which led to a worldwide shortage of contrast material, compromising the care of many patients globally. So years ago, I had an idea, which is, well, what if we could simply convert these non-contrast CT scans into contrast CTs without having to inject intravenous contrast? And this is when I started working with the engineers. Another important element of the equation. We had a really brilliant student who came and did his DPhil with us at the time. Cut a long story short, we demonstrated that, yes, we can, using aortic imaging and aortic aneurysm as an example. We show that by taking non-contrast CT images of these patients, and we apply AI algorithms of deep learning approach, we can synthesize the contrast enhancement upon the native CT image. And this was captured as a patent filing and subsequently led to a spin-out company, which I'm the co-founder and chief medical officer. And at the time when we published the paper, we really much focused on the aortic imaging aspects, but as this demonstration video will show you, the potential of digital contrast to enhance other type of soft tissues, small vessels, is clearly there. And what it requires, of course, is a lot of R&D work ahead of us. But this is where we're going to propose a complete revolutionary angle. We're going to change how the future of radiology is going to be conducted, of what we now coin a CT digital contrast. In life, this means no needle, one single scan, and we take that non-contrast CT scans, apply AI, and we show the digital contrast enhancement image. And really, you can start to imagine the potential patient impact and the potential improvement to healthcare delivery. But it's really the patient impact I want to focus on first. As being a clinician, that's what really drives us to work every day. And here I really want to show a little memoir or tribute to Reno Greenlaw. Reno was the director of innovation delivery at a local software engineering firm, the Oxford Computer Consultants. He was one of the first person in the world that I shared the concept and the initial pilot results with to show that digital contrast in CT scan could be done. Now, Reno was trained as a physicist. He had a PhD in physics. He totally saw the potential of this technology, and he was really driven to help me build that software prototype. We were meant to catch up for a pint after COVID, because I never met in person. But this was the last text that I received from Reno just before COVID ended. And it says, I had 3 contrast CT in a day, and now, it's only till now, he completely saw the value of our work, even though he knew the science was valuable. So it's based on this potential improvement to patient healthcare that I was able to draw together support from clinicians, industry partners across the globe, leading to the formation of what we call AICT Consortium, AI for CTs. We wanted to drive a common vision, which is to unlock the potential of CT imaging, and we use that to improve patients' clinical journeys and beyond. Now, this AICT Consortium is really an international collaborative. I have sort of leading radiologists helping me, Eric Ranchard, probably in the audience today, and also industry partners supporting to provide the infrastructure to deliver this consortium. And the principles are we're going to build a diverse data set so that we can drive the data science. We're going to provide a central infrastructure so everyone in the partnership can have access to the means required to develop data science on CT imaging. And it's going to be a very equitable partnership between all the partners. And this is collaborative research at its purest sense. So last year, after about 2 years of planning and lots of help from various data protection officers, research contracts office across different institutions on 3 different continents, including commercial partners, lawyers bouncing back and forth, we were finally able to sign the agreement between these 10 entities in 8 countries. So the AICT Consortium was officially formed, and we're aiming to double our clinical footprint this year. So how does this lead to any contribution or participation in net zero healthcare research? Well, you've heard what Dr. McAlister had presented earlier, the importance and important elements of the greenhouse emission by imaging. But here is the underlying message here sent by the policymakers. We now have what's in policy, the European Green Deal. So European Union have set the target to achieve net zero by 2050. So it's written into policy. And also notice focusing on the 2 bullet points below. European Union wants to promote economic growth decoupled from resource use, and that would increase the healthcare resilience. As I have mentioned earlier, reliance on manufacturing of a critical supply of healthcare products really can create problems in the domestic healthcare system. The NHS has the most ambitious goals to reach net zero ahead of the other healthcare systems. The target is to reach net zero by 2045, ahead of the pack. It's really in this context that we can start to see an emerging field of research that hope to promote this target on behalf of the NHS and the European Union. This editorial summarized what Scott had presented earlier. Global greenhouse gas about 5% from healthcare system, and out of that, 1% of global healthcare, global greenhouse emission is attributed by imaging. Taking CT scan as the example here, contrast CT has, as it turned out, huge environmental impact. A lot of them are being done, and the contrast CT scans especially, you have single-use products, consumables, the plastic waste, all of which have to be disposed of a single-use product. The energy consumption that Scott's already mentioned, not to forget that the contrast media that's injected into human body for each scan, it's all excreted into the environment. It's not absorbed, it's completely passed into the wastewater and actually constitutes the #1 pharmaceutical waste released by the healthcare system, because iodine, the active ingredient of contrast, as you know, can have toxic effects downstream. And therefore, by optimizing the CT digital contrast technology, we are aspiring to reduce the carbon emission of clinical radiology by about 300,000 tons in European Union, and up to maybe 1 megatons globally. This is a long-term goal, of course, but we have to start somewhere. So on the backdrop of this kind of new information and the formation of AICT consortium, we then looked amongst our peers and said, well, how can we together deliver some of the solutions for to achieve net zero healthcare? And this led to the formation of NetZero AICT Consortium, which includes the core members of AICT Consortium plus added expertise to address many other subsequent elements that's required in AI medical software as a medical device, from training, testing, implementation, all the way through to clinical deployment. If we look at the work packages or the tasks that we're going to deliver as a team, and we start off with gathering data from the hospital, and we create a diverse repository, which then is actively managed using a green computational pipeline for data curation, data model train validation, and we have an added team member capacity for life cycle analysis, which you've heard of just now, and also the health technology assessment, regulatory pathway landscaping. But most importantly, at the heart of this, what we need to make sure that as a team, the AI medical software that we create can be trusted by the stakeholders. So the core mission for the NetZero AICT Consortium, and actually for the AICT team together, we want to achieve trustworthiness amongst all the stakeholders, and that's underpinned by 3 key principles. We're going to have to adhere to all the legal frameworks, privacy, GDPR, etc. Of course, the ethics considerations and the regional, local regulatory approvals, absolutely critical. And in addition to that, we would have dedicated engagement with stakeholders, both in the patient, public sector, also with healthcare, and hopefully policymakers. So we have representation of privacy lawyers, ethicists, and communication experts helping us drive and deliver these goals. The second mission that we're going to achieve is developing the most diverse data set for CT scans in a centralized repository. Our aspiration is to reach 1 million CT scans from 3 continents by the end of this year, and the number will keep growing. Why centralized repository? Because anyone who deals with CT imaging or any sort of clinical imaging research would know that when you ask for scans from the hospital archives to do certain type of research, the hospital doesn't actually know exactly what kind of scan they have, because although the labeling on the clinical, what we call a CRIS or RIS, the information system, to say, well, this is a CT scan of the abdomen, maybe with contrast or without contrast. But the matter of the fact is sometimes the scans are done and the end result of the scan doesn't actually match what's described on the metadata. And the timing of the contrast scan could be mistimed, and therefore arterial scan become a venous scan. So really, in order for us to have access to the cleanest data set where we know what a scan is as labeled on the tin, we have to first centralize the data set, curate it, so that it is cataloged and research ready. So anyone who wants to reach a set of CT scans that fits a particular description, we can retrieve that within a very short period of time. And that will enable subsequent scale up of research at unprecedented scale. And the third key element to focus on is, of course, optimize and deliver CT digital contrast. Being a vascular surgeon by training, we've chosen angiogram as the first territory to conquer, partially because CT scans or CT angiograms is bread and butter of our practice, and it is diagnostic for most of the conditions that vascular surgeons treat. So amongst the consortium, the task would be to develop 5 indications for users of CT angiogram using deep learning. And here we describe a generative adversarial network architecture, which is published and very well accepted these days. But there could be new approaches that we're applying for the deep learning aspect. And we focus on optimizing CT angiogram of the aorta to pulmonary artery to cerebral vascular vessels, upper lower limb, and finally, as the final frontier, CT coronary angiograms, because of its envisaged level of difficulty. We're hoping to have learned enough information from the previous 4 tasks and help finally conquer the last remaining part of the anatomy. So here is how we could collectively scale and make an impact beyond research. Within the consortium, we have clinical partners across the globe. We have industry partners providing critical elements of data processing, data management for data science, down to the clinical validation in a CRO approach. And each of these clinical sites then, of course, becomes our local champions where we can beta test develop the algorithm. And because of the existing industry partnerships that have wide footprints into healthcare systems globally, here we have multinationals, SMEs across different parts of the world. We can rapidly scale up the deployment into once the algorithm has passed through the rigors of regulatory approval. So with this proposition, we were able to convince the European Union to invest in us, and we won a major Horizon Europe grant last year for NetZero AICT consortium to help deliver net zero healthcare system for European Commission. And here is a picture taken out at our kickoff meeting in Barcelona in December last year. And to wrap up this presentation, I thought to share with you an animation or video that we created to engage the public.
CT scans are examinations that we perform very frequently as radiologists, usually in hospitals, and we use them to get a better view of the inside of the body. For many CT scans, we inject contrast medium, and the purpose of this contrast medium is to enhance the body organs and, for example, also the blood vessels. It allows us to, let's say, interpret the images in a more accurate way.
About 300 million CT scans are done per year, and out of which about 60% requires contrast media. Now, the contrast CT scan itself is unsafe and uncomfortable to the patient. In terms of the environmental footprint, each one of these contrast CT scans requires a significant amount of consumables, such as the needle, the tubing. All of these need to be disposed of as a clinical waste. In addition, CT scans, particularly in the contrast CT, generates significant use of energy consumption. So a landmark paper in Lancet Regional Health last year had described the carbon footprint of each CT scan to be about 9.2 kilos. And that itself is just the carbon footprint of CT imaging, but there's additional element of the iodinated contrast when released into the wastewater actually constitutes the #1 pharmaceutical waste generated from the hospital healthcare delivery. During the NetZero AICT project, we proposed to establish the largest data repository of CT scans to further drive the data science to optimize what we call CT digital contrast. And CT digital contrast proposes to negate the requirement of contrast injection for CT scans.
Artificial intelligence will enhance the organs and also the blood vessels in a virtual way, because we don't inject any contrast medium. but the effect should be the same. And that would be a major advantage for the patients, of course.
Well, today there is almost an infinite amount of expertise and data in healthcare, but the problem is that it's often locked into silos. And in order to advance care, more collaboration is needed. For us, it was very important to have a centralized data repository in order to ensure the highest data quality and the long-term sustainability.
Modern clinical research requires both access and curation of data. And to maximize the volume and the quality of the data, NetZero AICT collects data from clinical partners in 3 different continents, all in a compliant framework.
By gathering all the data and expertise on one platform, we will build an ecosystem that will live for many years to come.
This project will run for 4 years. In the first 12 months, we focus on establishing the data repository and establishing the trustworthiness framework. In the next 2 years, we focus on optimizing the AI algorithms, followed by the clinical validation of 5 indications for users. In parallel, we're going to systematically examine the social and life cycle impact of delivering CT digital contrast and build a green and sustainable computational pipeline to enable long-term operation of other projects.
The trustworthiness of this project is built upon 3 pillars. The pillar of lawfulness, the pillar of public participation, and the pillar of ethics. It all starts with ethics. The project needs to be robust, safe, transparent, and has to have respect for the privacy of the data subjects.
Regarding the legal framework, one of the most important parts is protecting the privacy of the data subjects, and that should be done by design before the processing is conducted.
To ensure that this project is trustworthy, we are going to be engaging members of the public, patient representatives, in deep conversation about things like the level of accuracy required with the digital version of CT scans and a range of other questions. Crucially, members of the public are stakeholders, and we are inviting conversation to make sure this is done through co-design and co-production.
NetZero AICT is built upon European challenges. It's the rise in chronic diseases and increasing pressures on healthcare systems on one hand, and the environmental challenges on the other hand. So where there are challenges, there are also opportunities, and here comes NetZero, which delivers digital innovation to support the health systems, yet lowering the footprint of provision of the healthcare.
We really have an extraordinary team of people with a lot of expertise in all the facets that are involved in developing such an AI tool. We will not only take care of a high quality of the images or the data by which the algorithm is trained, but we will also think about the effect that it will have on the patient pathway.
So thank you. And that brings us to the end of the presentation. I think my colleague Anders had mentioned this is ecosystem building. Much more progress will be reported hopefully in the years to come.